There you go. All right. So let me. It's my pleasure to introduce Professor Pallab Dasgupta. He is from IIT Kharagpur, my alma mater, and also alma mater of a few of us in the Zoom here. And he's so was transiting to the Bay Area, and I thought it would be a great opportunity for him to sort of present what he's doing now. And it seems pretty bleeding edge. I know only a few of the words on the screen here, and only individually. Combined, I know even less than what it says. So I think I'll leave Pallab to sort of describe what he's saying, what he's doing, and I'll leave it up to him. So let me, before I go off on that, let me just start recording here so that it will go. Great. So the talk is being recorded, and here's Professor Dasgupta here.
Thank you very much for the introduction. Well, I mean, it's true that the title has a mixed bag of terms, and this is not really my main line of work. It is something that we are trying to conceive collectively in the Institute and trying to build more and more momentum on that. So it's all at a formative stage, and I thought that rather than talking about my primary line of work, which is more in the semiconductor and electronic design automation area, let me try to throw some ideas at some of the smartest minds in the industry from Google, and see how the reaction turns out to be. So as we know that before I start, of course, I mean, for those who do not know where Indian Institute of Technology of Kharagpur is, there are many IITs, and this IIT is on the eastern side of the country, close to Kolkata. It is the first of the IITs, has quite a large number of engineering disciplines, currently about 12,000 students. And it's a fully residential campus where you cannot do much apart from to study and do a few other things which are equally boring, perhaps. So this talk, as a disclaimer, will be very high level and technically shallow, and the intention is to outline a few things and if possible, open up a discussion. So I suppose that the IIoT revolution, that is the industrial Internet of Things, is something that is gaining in momentum, and there are a lot of things that are going to happen in the years to come. So as of now, when we talk about IoT, it is the human beings and the devices that we use that are connected to the internet, and we can do a whole lot of things using that. But what we expect in future is that all the machines, the appliances, like our cars, our home appliances, these are all going to be there on the internet, and increasingly a lot of control applications will be built over this kind of industrial Internet of Things. That means, for a computer science angle, there will be a huge amount of data that will get generated that can be used for various types of purposes, like health monitoring, for supervisory control, and a lot of other things. We cannot design cyber physical systems as we designed in the past because of this change that is going to come, and that is where I try to bring out a few points which are relevant for computer scientists to get involved, and in a domain which was predominantly mostly control intensive and a little bit of embedded systems. Right? So I will talk about this a little bit, and then a few other things that we are doing. So when we talk about the emerging picture of cyber physical systems, it has moved out from the traditional description of a control system where you have a plant which is controlled by a controller which is running on a processor. So increasingly we will have huge number of sensors everywhere. A lot of data will get acquired, and then there will be models for diagnostics, validation, control, and the whole ecosystem will develop around these things. There will be intelligent planning, decision support system, all of this in the control domain. For example, we will have smarter control of the power grids. We will have smarter control of the movement of trains in a yard, and so on and so forth. So I'll start by assuming that not everyone here is electrical engineer. So I'll just start briefly with the classical definition of embedded control. So we have a plant, that is the object which is being controlled. There may be multiple sensors which are periodically reading the variables of the plant. And there are the software tasks which process those sensor data. For example, when you're looking at an adaptive cruise control, the radar data will reveal that what is the distance to the lead vehicle, and that's a non-trivial amount of computation that goes into that task. And then once the scenario is known, then the control law is applied, which tells that in what way the control variables will change their values so that the plant is appropriately controlled. So a very important point here is that in the classical way in which we implemented control systems, the rate at which the sensors need to inspect the plant and the rate at which the software tasks need to process the data and the control law needs to be applied was something that the control engineer determined from control theory. For sampling in a particular granularity, you can design a controller using control theory. And then the embedded system designer's task is to ensure that all these software tasks are done periodically and on time, so that the control law execution is as prescribed by the control engineer. Now that was all very fine, because for every feature that we had in an embedded system, we had a dedicated processor. Now that has led to a situation where a modern automobile has easily 80 to 100 processors, because each feature, be it a power window or a power steering, it has its own sweet processor, and then that is implementing this control loop. Now, with the increase in the volume of things, and also with the increase in the number of non-determinisms that are going to crop up in this loop, that classical way of designing control will not work anymore. We need to relax the requirements that all tasks will execute periodically according to a fixed period, and we have to make it more friendly towards merging multiple controllers into sharing one or more processors. To give you an example of a real control system, if we look at an anti-lock braking system, and if you know what an anti-lock braking system does, so instead of applying the brake on the wheel, which may lead to locking of the wheel, an anti-lock braking system applies the brake in a pulsating manner. So it basically monitors a particular parameter called the slip ratio, and the slip ratio is the ratio between the translational velocity of the car and the angular velocity of the wheels. Now it may so happen that these two are not exactly the same, and the vehicle has a slip. It's actually skidding. Now, when a car normally moves, there is always an element of skidding which is happening, which we don't perceive as such. So the braking controller actually, its objective is to ensure that this slip ratio does not exceed a particular value. So to do that, it has these sensors like the Hall sensor and the MEMS sensor, which can the Hall sensor can actually monitor the wheel speed. The MEMS sensor can monitor the car acceleration, and then there are these two ECUs which can execute the control loops as indicated in the right side, and then these tasks are scheduled on the embedded processors, and they execute and implement the braking system. So this is a typical architecture in which such a cyber physical system would be implemented, that you will have operating system, typically a real-time operating system, running on what are called the ECUs or the processors, and then you have all these sensors. And the tasks are executed periodically in this manner. Now, an important goal that we started off with here was that if we want to relax this requirement that every software task has to be executed periodically, what ramification would it have on the control side? In the sense that how would the control that I'm trying to implement get affected by that? And curiously, today, if you ask this question to a control engineer, the control engineer does not understand the embedded system side of it, so it's not difficult for him to answer that. And if you ask this question to the software engineer, well, the software engineer does not know how the control is affected by it. So this, I'll skip to a couple of slides. So this connection is being established by a new theory which is developing. And what it does is, it tries to model the pattern in which the tasks are executing in terms of a language. Now, how do we get this kind of a connection? So to understand how this connection takes place, let us look at get a little more deep into the thing. So if I look at a plant, then the plant has some dynamics. That is, you can represent the dynamics of a plant by saying that, well, there is a set of variables xp of the plant, and you can determine the value of those variables at time t+1 if you know their values at time t, right? And the plant will evolve based on the control inputs, which the ut that it is receiving from the controller. So the plant variable xpt+1 is dependent on the plant variables at time t, and also dependent on the control inputs that it receives, that is ut, right? And then the controller also at every t instance, every time from t to t+1, it will study what are the plant variables, that is the yt, and based on that it will determine what will be the control variables at the time t+1. So you can think of this as a matrix that tells us how the controller is evolving, and this as a matrix which tells us how the plant is evolving. If you take the composition of these two, what you essentially get is a composed system, and this matrix that we show here, that is capturing the closed system dynamics of the control system. So that tells us that given the value of all the variables, that is plant and controller taken together at time t, what will be its value at time t+1. Now let us think at this from a scheduling perspective. So if there is a particular time t in which the controller is acting, that is, it is scheduled, it is going to update the control variables, then this matrix will be something. And in a particular time t, if the controller is not executing, if it is not scheduled in the processor for execution, then obviously the control variables will not change, but the plant variables will change because the actual system is evolving. The car is moving, so those variables will change. So therefore, you will have a different matrix for that. Now these matrices forms our alphabet. So you think of a language where these matrices are alphabets. So one matrix, say if I call that A1, is when the plant is executing, and the other matrix we can say is A0 when the plant is not executing, right? And now if I think of a language over this A1 and A0, then that language, I can reason about that language and say that which patterns of A1s and A0s are going to give me proper control and which ones are not going to give me the proper control, right? And then you can build an automata which tells you that what are the possible walks in the automata that is going to give you, appropriate control performance. This connection is very important, because once you have this connection, you can now throw away your standard requirement that every task has to be periodically executed. You can say that pretty much any random walk in this automata is fine, right? And that gives us flexibility, because tomorrow when we go into this Internet of Things and we have a lot of non-determinism, we cannot hold on to the traditional constraints that control system has to go through. So taking a cue from there, we look into a slightly more involved problem where we have to share a processor between multiple such systems. So you have two controllers, for example, and I have a switch that can execute controller 1 sometimes and controller 2 sometimes. So this is then the pattern in which the tasks are executing, and I get to see the execution of the controller, the two controllers in a time interleaved manner. Now, what is known is that if each of these controllers are individually stable, it may not be the case that their combination is stable. I mean, just to explain that why this can happen, you can look at this diagram which shows here. So from a very naive perspective, the kind of perspective that a computer scientist like me, who does not know much about control, would like to view, and my friend who is an electronics graduate knows much more about control. It's like this. So if you look at this, the figure on the left hand side, so that is our controller 1, and the trajectory that you are seeing here is the way the error is being damped. So there is a disturbance that has happened, and the error is being damped in a way. And any controller can be thought of as one which is damping some error. Like you want to keep a motor in a particular position, and whenever there is a jerk, it moves away, you bring it back into that position. Or you keep a vehicle in a particular speed, if it deviates from that speed, then that is a disturbance. So this one is bringing back the disturbance and damping it and reducing the error to 0. This one is also doing that, but now if you see that if I combine these two, that is in this region I apply controller 1, then again controller 2, then again controller 1, then you see that the error is actually building up. So the system becomes unstable. I mean, there is a nice example which we use when we try to explain that what is instability of control. It's a thing that we all encounter every morning when you try to fix the temperature of your shower. So if you turn the knob to the left, it becomes cold, and you turn it to the right, it becomes hot. Now, if you keep on turning vigorously to the left and right, you will have instability, because you will get cold, you will not be satisfied, you will get hot, you will not be satisfied, and this is instability. You just flip between two ends. But the real stable controller will be that you gradually bring it to the point which actually gives you the work. The important thing to understand there is the ability to arrive at the proper position is problematic, because the time it takes when you actually implement your action, that is you move the knob, and the right temperature water comes, there is a gap between the two. Why? Because there is this pipe, there is a length, there is a delay for the water to flow through the pipe and then to your body, right? So this delay aspect is something which can completely mess up a control system. And the delay typically will come from the execution side. That is, from the scheduling perspective, if I don't schedule the task on time and I get delayed, then a stable controller can become unstable because of this, right? So that is why the ability to formally establish that my controller will work under various patterns of scheduling, where there is different delays in the processing of the sensor data, is a very important emerging requirement, and that is the problem that we are trying to solve here. So now there are a few slides. I'm leaving these slides here, but I would not, as promised, go technically deep into these things. So I will be happy to answer questions later on if anybody is interested. There is a nice theory which has come up that connects the theory of schedules with the theory of control, and that is increasingly gaining in momentum, and there are these automata-based scheduling techniques which are being used to address this. So we are building tools around this space. We are seeing that there are multiple controllers that can share a processor, and how we can formally prove that these both the controllers are going to be stable and deliver the right kind of control performance at all points of time. Right. So I would like to move on to a few other things that we are doing in related domains, because this is a thing that I said was something that is evolving right now. It's a formative thing that we are doing right now, and we would like to involve with as many people as we can. The traditional bastion of our research group is on what are called formal methods or formal tools. To give you an understanding of what formal tools are, that if you take any real world system and you want to prove that it is correct, for example, if you take a program and you want to prove that the program is correct, you will typically run the program with a few inputs and check whether the outputs match with the golden outputs, right? But you cannot really, for any practical program, run it with all possible input combinations. So then how do you take a safety critical software which is going to go into your embedded application? And increasingly we are going to put more and more embedded applications in the healthcare sector, for example, for drug delivery and other types of safety critical tasks. We need to prove that the software is exactly correct, right? So how can you prove that a software is going to work for all possible inputs? So the key to such type of problems is that you treat the inputs as symbols. You don't assign values to them, right? You look at their domain and you treat them as variables, and then you do a symbolic propagation of the variables through the program and come up with a set of constraints which tells you that what is the post condition of the program, that if this program executes, then at the end of the execution these predicates will be true. And then you try to show that these predicates implies your requirement. If you can show that, then you have effectively symbolically established that the program is correct for all cases. So this is philosophically, quote unquote, what formal method will look like in the context of a program. In the context of an embedded system, when I have a physical plant integrated with it, it's more complex. It is more complex because apart from the discrete way in which software variables are upgraded, here you have real world systems which are evolving continuously with time. So again, there is a genre of formal techniques which can handle that kind of a system. So in the if you look at the safety standards for various types of domains like aeronautics, automotive, industrial process automation, nuclear, I've listed a few here. Each of these standards today has a mandate for using formal methods in proving certain things. There is a huge opportunity for computer scientists to work in this space. The reason being that these are all standards which recommend formal methods but are silent on how they are to be used, because that is the more difficult question. It's easy to do a recommendation, but then to implement that recommendation is difficult. So we are doing this recommendation and building prototype tools around certain very niche problems here. So I would like to talk about one or two to give you a flavor of the kind of things that people have to do from a computer science perspective, but going into a domain which is not their traditional area. So one such area is on railway signaling. So in the past, I believe many of you were not born at that time. We used to have manually operated signals. We don't have them anymore. In a railway signaling, can you tell me what are the types of things that the signaling equipment has to deliver, apart from, of course, making signals red, green, and yellow? There is another important thing that the signaling equipment does, and that is to determine that the direction in which the train will move, because between lines there are those point positions, right? And those positions where in old Hindi films somebody would get stuck and then that would create a climax, with the train approaching and all that. So those are also controlled by the signaling system. Now today a signaling system is primarily running on software, right? And this software which interprets the signaling is what in the railway terminology is called the security integrity level 4 software, which means that it has to go through extensive certification and then only it can be deployed. But the problem is that the ecosystem for developing railway signaling involves many different types of partners. For example, you buy the equipment from one particular vendor, but when you want to configure that for a specific yard, for a new yard, or you want to upgrade it for an old yard, the data corresponding to that yard is prepared by another team. That data tells us that which are the admissible routes, which are the sensors, the track segments in that route, and the sensors which sit on the tracks to detect whether a train is on that track. So all these things. So you can think of this as a precursor to an IoT kind of thing, because there are all of these different sensors which are gathering the movement of the train, and that goes into the signaling system, and the signaling system knows what the yard is about. But with this kind of a development, as late as 2009, in a particular incident in UK, which is reported in the literature, there was an incident where a collision was averted, where a train was given a movement authority, but then it realized that there is another train in front of it. So it turned out that the data that was used to configure the equipment was not correct, right? And then they did a thorough check of many yards in UK, and 5 other yards came up with similar data problems, right? And it's not isolated in UK, it happened in many countries. In Australia, there are reports of this thing. So how do you make sure that that data is correct? Because if that is not correct, then the entire signaling system, in spite of the software being proven to be correct, is typically not guaranteeing safety. So to do this kind of a thing, we went deeper into this, and you know what turned out is that the way the logic is defined in railway signaling follows a very old kind of paradigm, which we have seen in the past, called PLC. Yes, or in other words, it's called ladder logic. I'm sure that none of you have heard about ladder logic, right? So that used to be a type of logic that people used to use when they used to manually design circuits many years ago. You didn't have all these EDA tools and all that, particularly relay-based circuits, because we did not have semiconductor gates at that time. So they still use that kind of terminology because their manual processes are all built around that. See, in Google, you know what is the effect of legacy on doing new things, right? You encounter that all the time. So it was the same problem here, but it was also very structured. So that's why we could build a tool around that, and then take all these properties from railway signaling principles and prove it on these, right? Now this is going to a new scale in the future. In the future, we will have completely signal-less railways. You already have it in many metros, which are completely autonomous, right? And there is, I think, when we talk about autonomous vehicles, you have these autonomous trains. They will all evolve in one common way, and that is that there will be a huge amount of data that will go into the net from this, and that is already beginning to happen because. For example, in India, we have very old tracks, right? Tracks running since almost the British era. Now, it's very difficult to figure out that which track is developing a problem at which point of time, right? And you cannot afford to go and inspect these, millions of kilometers of tracks every now and then. So there is a ongoing initiative to see whether we can have sensors which can sense vibrations on the axles of the train. Now, if all these sensors are reporting vibrations at a specific location of the track across multiple trains, then you know that something must be happening there, right? So these are health monitoring issues that were not possible in the past, but now with this proliferation of the sensing and the IIoT kind of framework, it is going to be increasingly possible. So we work a lot on that space. We also work on purely software verification. We are validating a real-time operating system for an aircraft company, which is going to deploy that in near future. I have already talked about this. There is another area where this IIoT kind of application is already in place, and that is in the power grid sector. So in the past, monitoring power grids was a big problem, because it's a huge electrical system. So previously, when people used to sense the voltage, frequency, and the rate of change of frequency of voltages at various points in the grid, a standard problem was that how do you get a global snapshot of the grid? Because if you are not measuring them all at the same time, then there are a lot of disturbances happening all the time in the grid, so you will not get a picture, and those of you who are in distributed computing, you will have learned of the Lamport's algorithm for global snapshots. It's the same problem. How do you do that? So now here there are these devices which are called synchrophasers. Now these are increasingly being adopted everywhere in the world, including in the Indian power grid. So the thing that they do is they all synchronize with each other through a satellite and take the snapshot of all these parameters at exactly the same instance of time, right? And that is done several times in a second. And all that data from typically something like 3,000 to 4,000 sensors will now be pumped into the National Load Dispatch Center. Now, it's a good thing and a bad thing. In the past, people, it's also like the thing that we have become hypochondriacs after a lot of medical data have become available in the net, right? These days anything happens, we go to the net and start checking there. So in the past, the load dispatch centers were blissfully unaware of what is going on, right? Now they did not. They were not seeing any disturbances that they are now seeing. Now what is happening is suddenly in some PMU they see a glitch, and maybe a similar glitch in nearby PMUs. That gets them worried because they now try to figure out what is happening, right? This is a very difficult problem because if you know what is your fault, you can simulate the fault and find out that what is the effect of that fault on the patterns of the disturbances that you will see on the PMUs. But if you see the patterns of disturbances, the reverse map is not so easy to do, right? And that involves a way of formally trying to establish that which is causing what. It's a standard problem of learning decisions. So you figure out that if this and this is observed, then you decide that is the error that has happened. And sometimes what happens is that it might be even a noise which is causing this. So this is another area where there is a lot of opportunity. We are working on this with the National Load Dispatch Center of India and trying to see how we can formally establish. This is a picture of the Load Dispatch Center, but it is only one wall that you are seeing. It actually looks more like a Hollywood movie thing with panels all around the room, and you can see pretty much any bus in the country, and you can see what is the voltage, current, etc., and the load on those lines. So this slide kind of summarizes what we are doing in this area. Again, these are large-scale cyber-physical systems, increasingly becoming more complex. Okay, this is our traditional domain in which we have been working for around 20 years or so. Our website has a lot of information on this. I'll skip through. But I'd like to talk a little bit about this thing. This is a new thing that we are doing. That we are trying to look at music from a formal perspective. I mean, this has got nothing to do with cyber physical systems unless you think of the connection between the musician and the audience as a cyber physical connection, and that is actually a very interesting connection, and there's a lot of scope of doing cognitive research and other things in that domain. But we are trying to do a much less ambitious thing. Well, music is fundamentally a language, because in most part of the world, every music is all about an octave, which you have 14 notes, and when you are rendering a particular piece, then it's actually a string over this alphabet of notes, right? Now, if you look at it from a language perspective, particularly in the Indian music context, in the Indian music, there are certain things called ragas, and those ragas have a grammar, and the grammar, as of now, is very loosely specified. In the sense, if you think of it from a string point of view, the grammar of the rag only tells you that out of the 14 notes, which ones are there in your raga, and it tells you that which sequence of notes you can use in the upward movement and which sequence of notes you can use in the downward movement. It does not tell you when you are going to go upward and when you are going to go downward in the frequency spectrum. So that is something which people learn through years of training from their gurus. Now, in India, that classical tradition where people used to spend so much time with their gurus is slowly becoming infeasible, and now very few people actually do that. So the challenge here was that how can we preserve this thing? How can we preserve those unwritten structure of the rag, which the guru explains to the student through example rather than through a proper grammar. So that is what we refer to as the deeper structure of a rag, and we try to learn that. So we try to create take phrases. We try to notate from existing renditions using signal processing techniques, and then try to learn this hidden structure of the rag. So it's probably the most risky project that we have taken up, because when science goes into the realm of humanities and arts, that is where it is most vulnerable, because the way that you understand arts is from a completely different understanding, and unless that matches with what you are doing from the scientific perspective, it really does not cut much of the ice. Okay? Okay, so that's pretty much what I had to discuss. As I said, that it's an informal discussion on various things. This is a picture of our lab and a few members of our group. Not everybody is here, though. Thank you very much.